all the covalent bonds have some partial ionic character. Okay? The ionic bonds also have partial covalent character. The partial covalent character of ionic bonds was discussed by Huygens in terms of the following rules. Okay? The smaller the size of the cation and the larger the size of the anion, the greater the covalent character of an ionic bond. Do you understand what I am saying?
Yes, sir.
The greater the charge on the cation, the greater the covalent character of the ionic bond. Okay?
Okay, sir.
For cations of the same size and charge the ion, I repeat, for cations of the same size and charge, the one with electronic configuration n-1, D0, NS0, typical of transition metals, is more polarizing than the one with a noble gas electronic configuration NH2NP6, typical of alkali and alkaline earth metal cations. Okay?
Okay, sir.
The cation polarizes the anion, pulling the electronic charge toward itself and thereby increasing the electronic charge between the two. Okay? This is precisely what happens in a covalent bond, that is, build-up of electronic charge, electron charge density between the nuclei. The polarizing power of the cation, the polarity of the anion, and the extent of distortion, that means the polarization of anion are the factors which determine the percent covalent character of the ionic bond. We have discussed earlier, we are repeating. Okay. So, in summary, you can say the polarizing power of cation will be higher if the charge on cation is high or higher and the size of the cation is smaller. That means the smaller the cation and higher the charge on cation, that will strongly polarize this orbital. Is it alright?
Yes, sir.
That's why, according to Huygens rule, when the cation is of smaller size and anion is of larger size, okay, there will be more percentage of covalent character in the bond constant. Is it alright?
Yes, sir.
Yes, sir.
So, we will now discuss about the other oxides. Okay? We now discuss second period oxides. Okay? Lithium oxide, beryllium oxide, boron trioxide, carbon dioxide, nitrogen pentoxide, oxygen does not have any oxide, and fluorine does not have any oxide because F2O is not an oxide. It is F2 is not an oxide, it is called oxygen fluoride. Okay?
Okay, sir.
Because fluorine is more electronegative than oxygen. So, if we consider the second period oxides, the nature of oxides is such that basicity decreases in which direction? From left to right. Okay. That means acidity of the oxide increases. Is it clear to you?
Yes, sir.
Both of you?
Yes, sir.
So, same case will be observed in case of sodium oxide, magnesium oxide. These are period 3 oxides. Okay. Aluminum oxide, silicon dioxide, phosphorus pentoxide, sulfur trioxide. We are taking the higher oxides of the elements concerned. Okay. And Cl2O7. As we move across from left to right, you see this is alkali oxide, alkali metal oxide. This is alkaline earth metal oxide. Okay?
Okay, sir.
So these two are basic in nature. Here only this is basic. This is amphoteric. Amphoteric. Do you know what is amphoteric? Amphoteric. That means ubodharmi. Okay? This is slightly acidic, weaker acidic. Weakly acidic. Okay? This is also weak acidic oxide. Yes? This oxide is strongly acidic. Okay, this is to be not considered because it is not oxide, it is fluoride. Okay, so from left to right, we have studied that lithium oxide is basic in nature, beryllium oxide is amphoteric oxide because it can react with acid as well as with base. Okay, B2O3 is weaker acidic oxide because it does not dissolve in water, but it can react with NaOH to produce sodium metaborate. So it can be considered as acidic oxide, though it is an weaker acidic oxide. Okay. Carbon dioxide is also weaker oxide, but not so weaker like B2O3. Okay. When carbon dioxide dissolves into water, it dissolves in water. When carbon dioxide dissolves in water, produces, we know, carbonic acid. That is H2CO3. Similarly, when N2O5 dissolves in water, produces strong acid, nitric acid. Do you know what is nitric acid? Okay. Balance is complete. Is it all right?
Yes, sir.
So, we have clearly explained what about the second period oxides. Is it all right?
Yes, sir.
In case of third period oxides, you see sodium oxide and magnesium oxide. The sodium oxide, lithium oxide, these are alkali metal oxides. Beryllium oxide and magnesium oxide are alkaline earth metal oxides. In this case, in case of period 3 oxides, sodium oxide is strongly basic. It is more basic than magnesium oxide. Because sodium oxide when dissolves in water produces caustic soda. That means NaOH. But MgO, when dissolved in water, produces magnesium hydroxide, MgOH will produce. Okay. But aluminum oxide does not dissolve in water, but it can react with HCl to produce aluminum chloride, that means LCl3, and when reacts with NaOH, produces sodium aluminate, NaAlO2. You know what is NaAlO2? You read in Madhuri. Okay. Similarly, silicon dioxide can react with NaOH to produce sodium silicate. What produces? It produces sodium silicate with NaOH. It produces AlCl3 when dissolved in acid, that means hydrochloric acid, and sodium aluminate when dissolved in NaOH. Okay. P2O5 when dissolved in water produces phosphoric acid. That's why it is phosphoric acid. Okay. H3PO4. That's why it is strongly acidic. It is more stronger. This produces in water H2SO4 is well-known acid, king of acid. You know, but when Cl2O7 dissolved in water produces more stronger acid, and which is the strongest acid among the periodic element oxides. Okay. In periodic table, whatever the oxides may be, out of all these oxides, Cl2O7 is the most acidic oxide because it produces strong acid, that means HClO4, that's called perchloric acid. Perchloric acid. Acid may be written as A bar. Okay. So, we have clearly discussed period 2 oxides and period 3 oxides. Now we will consider what will happen in a group. Okay. We have discussed already Li2O, Na2O, K2O, CH2O, etc. Okay. Similar case can be seen in case of beryllium oxide, magnesium oxide, calcium oxide, strontium oxide, barium oxide, etc. Down the group, basic nature will be higher. Okay. So we need not to discuss further. But in case of any group for p block elements, look at the oxides, SiO2, SiO2, nature of the oxide down the group, basicity increases, acidity decreases. Acidity decreases. Here another example, Cl2O7, Br does not form O7, BrO5. Okay, Br2 O5. Down the group, the acidity here also decreases. Okay, in case of phosphorus pentoxide, Avabit L2O5, AS2O3, is it alright? SB2O3. These are group 15 oxides. A2O5, P2O5, AS2O3, SbO3. Down the group, basicity increases, acidity decreases. That's why H2O3 is amphoteric oxide. For this reason, this is amphoteric. That means hypothermy. Okay? Amphoteric oxide. Okay? So, total picture we have found. Is it alright?
Yes.
Yes, sir.
Now come to the point. For a particular oxide, you see, if we consider all the oxides of nitrogen oxides, okay, nitrogen, what will you see? N2O, NO, N2O3, N2O4, N2O5. Write down the oxidation numbers. It's +1, that is of nitrogen, okay? +2, +3, +4, and +5. These two are neutral oxide, you know? Do you know?
Yes, sir.
These are neutral oxide. Weaker acidic oxide.
Yes, sir.
This is mixed anhydride. I will discuss what is mixed anhydride. Mixed anhydride stronger than this, okay? Not so weaker, stronger than this, but weaker than this. This is stronger acidic, strong acidic oxide. Is it alright?
Yes, sir.
Okay. What is the reason behind this? You have to remember that oxidation number of central metal. Okay. Higher the oxidation state, I am writing here. I can write here. Higher the oxidation number of here nitrogen, okay, nitrogen, higher will be its acidity. Do you understand?
Yes, sir.
Yes, sir.
Okay. Not only in case of nitrogen, this is a general rule. Okay. Higher the oxidation number of the central atom, higher will be its acidity. I have discussed only the case of nitrogen. There are so many cases. Okay. We can consider other cases also. Suppose phosphorus oxides. Okay. In case of phosphorus, you don't have so many number of oxides. There are P2O3 or P4O6. It can be known as P4O6, same oxide. Dimer of P2O3 is P4O6. I am considering only two oxides, P2O3 and P2O5. These, when dissolved in water, produces H3PO3, but this one dissolved in water produces H3PO4. You know, H3PO4 is stronger than H3PO3. Okay. I have to explain what is mixed anhydride. I have forgotten. Okay, what is mixed anhydride? You see, if N2O4 dissolves in water, produces two acids, okay, HNO3 and HNO2. Okay, when dinitrogen tetroxide, N2O4 is known as dinitrogen tetroxide. When dissolved in water, produces nitric acid as well as nitrous acid. Nitric acid is stronger acid than nitrous acid, but both are strong acid. More or less, nitric acid is more or stronger than nitrous acid, because in nitric acid, oxidation of nitrogen is +5, but in nitrous acid, oxidation of nitrogen is +3. You see, when an oxide in dissolving in water produces two acids, these type of oxides are called mixed anhydride. What is anhydride? What is? Do you know what is anhydride? If we drag out water from sulfuric acid, what will happen? What you will get? Sulfuric, the formula of sulfuric acid is H2SO4 minus H2O. You will get SO3. Is it alright? That means sulfur trioxide is the anhydride of sulfuric acid. Is it clear to you?
Yes, sir.
Vice versa. When sulfur trioxide dissolves in water, produces sulfuric acid. When we absorb the water of sulfuric acid by using an water absorbing substance like phosphorus pentoxide, or it may be other dehydrating agent, water is eliminated from sulfuric acid and produces sulfur trioxide. So my question is, what is the anhydride of sulfurous acid? Can you tell me?
No, sir.
Why not? You just minus H2O from H2SO3. Try. Yes, exactly. Okay. Sulfur dioxide when dissolves in water, you see, sulfur dioxide when dissolves in water, it produces H2SO3. That's why sulfur dioxide is the anhydride of this. Okay. Another example, you see, I am writing some metal oxide. Okay. But their oxidation numbers are different. For example, I am taking manganese. Okay. So these oxides are possible for manganese. Okay. MnO, Mn2O3, MnO2, Mn2O7, etc. You see, this oxide is basic. You see, where the oxidation number of manganese is +2, here is +3, here is +4, here is +7. Okay, so if we go from left to right, it will be an acidic oxide. Do you know it is acidic oxide? Have you any idea why it is an acidic oxide? Because when Mn2O7 dissolves in water, produces HMnO4, that is permanganic acid. Okay,
Yes, sir.
this is strong acid, permanganic acid. This is strong acid. That's why Mn2O7, though it is a metal oxide, but it is acidic oxide. Similarly, in case of chromium, I am writing only 3. Okay, for saving the time. You see, this is basic. This is acidic, but less acidic. Okay, but it is strongly acidic because when it is dissolved in the water, produces H2CrO4, which is a strong acid, chromic acid. It is a chromic acid. So we got here two strongly acidic oxide. One is Mn2O7, both are metal oxide, and another is CrO3, chromic oxide. This is also called chromic anhydride because it produces chromic acid. If we dry out water from chromic acid, we will get CrO3. Okay. We have discussed various types of oxides, metal oxides, non-metal oxides, and also we have got some amphoteric oxide like As2O3, Sp2O3. These are amphoteric oxide because they can react with both acid and base. Okay.